Next we have exercise 8, and in this one we have to prove that for every positive integer n, the sum of the reciprocals of positive divisors of n, which is the left hand side, equals sigma of n divided by n. That means this is equal to the sum of the positive divisors of n divided by n. So let's see the solution. So here's the solution, which is surprisingly simple. It's almost a one-line solution. As d ranges over all the positive divisors of n, so does n divided by d. And because of that, the summation of all these quantities n divided by d, as d varies over all the positive divisors of n, is actually just the sum of all positive divisors of n, which of course is sigma of n. And then what you do, you divide both sides by n, so that gives you this. But still, in order to better understand exactly what is happening here, let's see one small example. The solution is over here, but now we want to understand it better. So let us take a small value of n, but also at the same time not too small. Say n is equal to 6. Then if we write what sigma of 6 is, it is the sum of all positive divisors of 6. And the positive divisors of 6 are 1, 2, 3 and 6. So it's just that. And then you notice that you can write 1 as 6 divided by 6, 2 as 6 divided by 3, 3 as 6 over 2 and 6 as 6 over 1. So the real meaning of what we wrote here is this. What did we say? That as d varies over the set of all positive divisors of n, so d is a variable, right? And it takes all the positive divisors of n as its values. As it does so, then the variable n divided by d also takes all the positive divisors as its value. N divided by d is also a variable, where n of course does not change, but d is changing, so ultimately the quantity is changing. So that is why if in place of d we write n divided by d, then actually now we are going from this back to this. So if I start with this sum and I change d, then ultimately I again actually get all the positive divisors. That is why this sum is also equal to sigma of n. So that's the explanation. Let's go to another one. Next we have 10. Establish the assertions below. Assertions. There are two other parts which we will consider afterwards. First, let us see what part A is and let's solve it. So the assertion here is this. A positive integer n is given which is greater than 1. So by the fundamental theorem of arithmetic, it will have a prime factorization, and say that prime factorization is this. There is of course no need for me to again tell you what these things are, you already know very well. And then these inequalities are true. 1 is greater than n divided by sigma of n, sum of positive divisors of n, which itself is greater than this product, where the general term in the product is 1 minus 1 divided by pi, where these pi's are of course the primes in the prime factorization of n. So let's now establish these identities. In this solution, we are first of all going to prove this one, and then we will go to the other inequality. So the first thing we note about n is that n is greater than 1, and that is why since n is greater than 1, there are at least two positive divisors of n, and here 2 means two distinct, 1 and n, and this is true even when n is a prime number. At least these two are there, there may be others or may not be others. And because of that, the sigma value of n, the sum of positive divisors of n, will be at least 1 plus n. Actually, if you write sigma of n fully, then all the positive divisors are added up, but say from them you keep only 1 and n. So then likely you are writing less, but you may actually be writing all the positive divisors because n may be prime. So in general, sigma of n is greater than or equal to 1 plus n, and that means it is strictly greater than n, because now if you ignore 1, then you get strict inequality. So that means sigma of n is greater than n. Now if you divide both sides by sigma of n, then you get this inequality. And you can, because sigma of n after all is a positive integer. It's a positive real number. And next we are going to prove this one. So let's see. So next what we do, we multiply sigma of n by this product, that other part of the inequality. And then we write what sigma of n is by what we already know about sigma of n. We know that whenever there is a prime factorization of n when it's given, then sigma of n in terms of that prime factorization is this. This we already know. And each factor here, each term in this product looks like this: pi to the power ki plus 1 minus 1 divided by pi minus 1 times, it doesn't end here of course, times this thing, where we did a little calculation. In place of 1 minus 1 over p1, we can write p1 minus 1 divided by p1. Similarly, the other factors. Now you can see that I have not actually written the term corresponding to p2. It's not necessary that you have to write 1 for p1 and then p2, and then only you can use this ellipsis dot dot dot. If you have run out of space, then you can write like this also. The pattern obviously is clear. Now the thing is that you can cancel this p1 minus 1 and this p1 minus 1. Similarly, the other factor that I haven't written, which involves p2, there also you have p2 minus 1 as the denominator. And here also, after this factor, there is p2 minus 1 divided by p2. So there will be a cancellation there as well. Similarly here, pr minus 1 and here pr minus 1 will cancel each other. So after you do those calculations, those cancellations, then you are left with this. So we are writing p1 below this, whatever is surviving in the numerator. Similarly, the other factors are also written, and finally this one divided by that PR. And now if you further do the divisions, you get this. Now if you do not write this minus 1 over pi and simply write, I'm talking about the general term in this product, in place of pi to the power ki minus 1 over pi, if you write simply pi to the power ki, that means you are not subtracting a positive real number. All these 1 over pi's are positive real numbers, which means you are writing more. So this thing is less than this product, which however is n. So all now you have to do is you divide both sides of this inequality by sigma of n, which inequality, that this is less than n. So that way you get the inequality that this thing is less than n divided by sigma of n, which is our second inequality. So that way you will get it. So I haven't written that, you do it yourself. So that is part A. Next let us see what we have in part B. So this is part B, and the assertion here is that sigma of n factorial divided by n factorial is greater than or equal to the sum of the reciprocals of the first n positive integers. And n of course is any positive integer. So let's see the solution. This solution is instant. Just like that you have solution. By exercise 8, with exercise 8 at our disposal, we can just instantly write this sum in place of sigma of n factorial divided by n factorial. So it is the sum of the reciprocals of all positive divisors of n factorial. Now, among the many possible positive divisors of n factorial, depending on n of course, in particular we have these 1, 2, 3, all of these divide n factorial because they appear as factors when you write n factorial fully, when you write what it is, all the way up to n. So obviously those reciprocals will also appear in this sum, plus maybe other things will also appear which are also positive divisors of n factorial. So if we ignore the other things and only consider these things, then maybe we are considering less, maybe not. That is why greater than or equal to this. And that's because whatever else you have to write in this sum to get the sum fully, all of them are positive real numbers. So by ignoring them, maybe you are writing less. That's why we have this type of inequality. And that's it. Next we have part C also. In part C, we have a composite number n. Obviously it's greater than 1. Then we have to prove that its sigma value is strictly greater than n plus square root of n. So let's solve this. Alright, so we start the solution by considering the composite nature of n, and because of this, n has a non-trivial positive divisor, say d, which we have written like this. Because n is composite, there exists an integer d which is greater than 1 and less than n, and d divides n. Okay. Now obviously either d is less than or equal to square root of n or d is greater than root n. Exactly one of these two things will happen. Say d is less than or equal to root n. Then you divide both sides of this inequality by n, so you get d over n less than or equal to root n over n, or d over n less than or equal to 1 divided by root n. Or, now if you take the reciprocal on both sides, then the inequality will get reversed, it will change direction. So you will then have n over d greater than or equal to root n. Alright. So actually what do you see here? You see that either you have a divisor d of n that is greater than root n, or if that's not the case, then you get another divisor of n which is greater than root n, actually greater than or equal to, and that another divisor is n divided by d. Just like d divides n divided by d also divides n. And there is one more thing. Note that both d and n divided by d are neither 1 nor n. Why? Well, d already is neither 1 nor n because of the choice. And what about n divided by d? N divided by d cannot be equal to 1, because otherwise n would be equal to d, which is against this choice. Also, n divided by d cannot be equal to n, because otherwise d has to be 1, which goes against this strict inequality. So both d and n over d are non-trivial divisors of n, positive divisors, and at least one of them is greater than or equal to square root of n. Either it is d or it is n divided by d. Now we are going to use this fact. So if this is the case, if d is greater than root n, then how can you relate sigma of n, d and n? You see, you are actually already getting 3 positive divisors of n. 1 and n are always there. Besides them, you also have d, but there may be others. That is why we have this inequality. Sigma of n is at least 1 plus d plus n. But already d is greater than n. So if you replace root n. So if you replace d by root n, then you are writing less. And on top of that, if you ignore 1, if you remove 1, then you are actually writing even less. So sigma of n is greater than n plus root n. This is what you wanted to show, right? But that is only one case. In the other case where d is less than or equal to root n, we have already seen that in that case n over d is greater than root n. Now n over d, just like d is also a positive divisor of n other than 1 and n. So in this case, just like that case, you can write sigma of n greater than or equal to 1 plus n divided by d plus n. And now this is greater than or equal to root n. So you may say that why I did not, you may ask why I did not write this equality sign here. That is because even if n over d is equal to root n, but there is this 1 which I am not writing anymore, so I will have strict inequality, and that way in this case also we get sigma of n greater than n plus root n. So that completes this exercise. And let me end this video here itself. There are other exercises also ahead, so that we will solve next week. So until then, this is me, Lucifer, from A Mathematical Room. Have a nice day.